Okay, for evaluating limits, direct substitution is often the best strategy and it works most of the time, but there are occasions when it does not work. So for this first one here, it says the limit of, as x approaches 6 of f of x, if it were to equal 0 over 4, 0 divided by 4 is just 0. And I could evaluate that limit. The limit as x approaches c of f of x, if it was 4 over 0, I know that's undefined, so I know that that limit does not exist. I might be able to explain why it doesn't exist better, but I do know the limit does not exist. Now the third case is, what if the limit as x approaches c of f of x is 0 over 0? Okay, does that equal 0? Does it equal 1? Does it not exist? This is what we call an indeterminate case. Now, indeterminate doesn't mean that's the answer. Indeterminate means I have no idea. You need to do more work in order to find the limit. So if you get 0 over 0, you're not done. You need to find a new strategy that will work to evaluate that limit. Okay, so the first strategy we're going to look at is factoring. Okay. Now, the only time you need to use one of these strategies is if you get 0 over 0. So I would first, at least if it's easy in your head, plug it in your head to see if it's going to be indeterminate. Okay, so the limit as x approaches 2 of x minus 2 over x squared minus 4. Let me think. If I plug in 2, 2 minus 2 would give me a 0 in the numerator. At the denominator, 2 squared is 4, 4 minus 4 is 0. So because I'm getting 0 over 0, direct substitution is not adequate to evaluate this limit. So I'm going to factor it. Now, as you're simplifying this expression, you need to keep writing the limit as x approaches 2, and you keep writing it until you actually do the direct substitution step. Okay, now I'm going to go ahead and cancel out the x minus 2's. And I can do that because x will not equal to 2. It will approach 2, but it will not actually equal to 2. So I'm left with 1 over x plus 2. Okay, let me cross those out. Okay, now let me see if direct substitution will work now. Now that I'm doing the direct substitution step, I can plug the 2 in directly. If I plug in 2, 2 plus 2 is 4. So the limit is actually 1/4, even though at x equals 2, the value doesn't actually exist. Okay, I'm going to go ahead and look at example B. Okay, before I move forward, I want to first think about if this will actually be indeterminate. You can't always factor anyhow, and you can cancel out factors if it makes it easier to evaluate, but it's just not always necessary. So if I plug in -1 in the numerator, I get positive 4 minus 12, which is going to be -8. So I can actually do this problem. So let me just go ahead and do direct substitution. If I plug in 4 times 1 minus 12 in the denominator, what is that? 1 minus 4 plus 3. Okay, and once I do the direct substitution step, I no longer write the limit as x approaches -1. So that's going to give me -8 over 0. So I know that this limit does not exist. Now, if I had wanted to factor it, I could have factored it as well. I would have come to the same conclusion that the limit does not exist. Okay, let me go ahead and do the next one. Okay, let's see, I want to plug in x as -2. Now, I probably want to try direct substitution first, but to be fair, you could factor it first because sometimes factoring just makes it easier to evaluate. Okay, if I plug in -2, what do I get? I get -8 minus 4 plus 12. So I do get a 0 in the numerator, and I get 4 minus 4. This is going to be 0 over 0. So I'm going to go ahead and factor it to make it better. Okay, I am going to keep writing the limit as x approaches -2 because I have not yet evaluated the eliminate, or I haven't done the substitution step. Okay, and again, sometimes you might just want to factor because it's easier to plug into anyhow. I think it's easier to plug into factored form than the original. Okay, so can I cancel something out? Yes, I can cancel the x plus 2's. I could also cancel the x's. They're not really causing me any trouble, but to make it easier on myself, I can. Okay, I'm going to bring it down here. So I'm just left with x minus 3. So if I plug in negative 2, I get the limit is negative 5. And again, the value of the function at negative 2 is not defined, but the limit does exist because as I approach it, the graph is doing some conclusive behaviors. Okay, the next strategy for dealing with indeterminate limits is using conjugates. It'll often look something like this, has some kind of radical in it. Okay, now remember, you only have to use these strategies if you have an indeterminate limit. So let me see if this is actually going to be indeterminate before I try to use the strategy. So I'm finding the limit as x approaches 1. So if I plugged in 1 in the numerator, 1 minus 9 is negative 8. So this is going to be, this won't be indeterminate. So I can go ahead and do direct substitution. So I get negative 8 over negative 2, which is positive 4. So that was easy. Again, if there is no reason, if direct substitution works, use direct substitution. It's always going to be the fastest method. Okay, let's try this one. If I plug in 4, 4 plus 5 is 9, the square root of 9 is 3, 3 minus 3 is 0. Okay, numerator 0. If I plug in 4 in the denominator, 4 minus 4 is 0. 0 over 0 is indeterminate. So in this case, I am going to need to do something to make this better. I am going to multiply by the conjugate. Now I'm going to plug in, so I don't care about rationalizing versus not rationalizing, square root on the top or the bottom. So I'm going to look wherever the square root is. It currently happens to be in the numerator. Okay, I'm going to multiply that by its conjugate. So instead of root x plus 5 minus 3, I'm going to multiply it by plus 3. If I do it to the numerator, I have to also do it to the denominator. Okay, let's go with this. Okay, so limit, I'm still writing limit because I write it until I do the direct substitution step. Okay, now if I do root x plus 5 minus 3 times root x plus 5 plus 3, this is a difference of squares. So root x plus 5 times root x plus 5 should cancel out the root x plus 5 and turn it into just x plus 5. And then if I do minus 3 times positive 3, I get minus 9. Okay, for the denominator, I'm going to leave it in the format it's in. So it has the x minus 4, put it in parentheses because these are factors. I'm just not distributing them out because they're not going to turn out in a way that will help me. Okay, I'm going to simplify the like terms in the numerator, and I'm still writing the limit as x approaches 4 because I have not done direct substitutions step yet. If I do x plus 5 minus 9, 5 minus 9 is minus 4. So what am I left with? X minus 4 in the numerator. The denominator, I'm going to leave it the way it is. Okay, now that I've done this and I've multiplied it out, I see that I can cancel the x minus 4's. And if I've done it right, there should always be something that will cancel that will help me evaluate the limit. So I'm left with 1 over root x plus 5 plus 3. And then make sure you take it all the way to this simplified format before you do direct substitution. So now I'm going to do direct substitution. So I don't have to write limit anymore because I'm going to plug it in. So if I plug in the 4 plus 5 plus 3 equals 1 over root 9 plus 3, so 1 over 3 plus 3, which is 1/6. Okay, the third strategy for dealing with indeterminate limits is to use trig identities. Okay, but remember, we only use these strategies if I get an indeterminate limit, which is 0 over 0. So I always want to check first, because otherwise it's a lot of work. Okay, so for this first one, if the limit as x approaches 0, see if I do the sign of 0, it is 0, 0 squared 0. What about the denominator? What's the cosine of 0 is 1. So this is, I can do direct substitution here. It's going to work. Okay, the sine of 0 is 0 squared. 1 plus the cosine of 0 is 1. So I get 0 divided by 2, which is just 0. So I could use direct substitution for that particular problem. Okay, let's try the next one. If I were to plug in pi over 2 in direct substitution, the cosine of pi over 2 is 0 squared 0 times 5, 0. Okay, the sine of pi over 2 is 1. So 2 minus 2 times 1 is 0. So this one is going to be indeterminate. So I'm going to have to work with this. Okay, these are the identities we most often use, the Pythagorean identities, which you probably know fairly well, and the double angle identities sometimes come up. Okay, I'm going to keep writing limit until I do the direct substitution step, but I'm not doing it now because I'll get 0 over 0, which won't help me. Okay, I am going to, let's see, the denominator has sine in it, so I'm going to do a substitution for cosine squared. Remember, cosine squared is the same as 1 minus sine squared. Okay, and the denominator, I'm going to go ahead and take out a common factor. So I can take out the 2. Okay, there's nothing I can do quite yet, but I can see that I can factor this expression more. So I'm going to go ahead and factor that expression more. Okay, can I cancel anything now? I can cancel the 1 minus sine x. So hopefully that fixed our problem. Let me bring down what I have left. And I am still writing the limit as x approaches 2. And I will do it all the way until I get to the direct substitution step. Okay, let's try to plug it in now. Okay, 1 plus, what's the sine of pi over x? 1. So after all that work, I got the limit as x approaches pi over 2 is 5. Okay, let's look at C. What do we have? The limit as x approaches pi of tangent squared x over 1 plus cosine x. The tangent of pi is 0. Cosine of pi is -1, so 1 plus -1 is 0. So I am going to get an indeterminate limit here. So I'm going to have to do some work. There's many ways to work with these. I think I'm going to turn it into sine and cosine, although multiplying by the conjugate I feel like would be a really good strategy as well. Okay, I'm going to change tangent squared into sine squared over cosine squared. Okay, let me rewrite this. I don't like the complex fraction. Okay, so I'm doing sine squared x over cosine squared x divided by 1 plus cosine x, which is multiplying by the reciprocal. Let's see, I see a lot of cosines in here too, actually. I'm going to rewrite sine squared as 1 minus cosine squared while I do this step. Times 1 over 1 plus cosine x. Okay, I can see now if I factor the 1 minus cosine squared x, I will be able to cancel something, and hopefully that will be enough. Those cancel. Let me bring over what's left. I mean, you do need to show your steps, and you need to keep writing limit all the way until we get to the direct substitution step. So what am I left with? I have 1 minus cosine x in the numerator. And in the denominator, I have cosine squared x. Okay, make sure you go all the way till you get the simplified expression, and then I can go ahead and do direct substitution. So 1 minus the cosine of pi over the cosine of pi squared. The cosine of pi is negative 1. Okay, so the limit as x approaches pi of that expression is 2. Okay, let's do one more trig one. You could have also done the previous one using different strategies. It would have still gotten the same result. So I'm trying to show you different types of problem to see which one you prefer. Actually, maybe I'll do this one 2 ways. Okay, this one's going to have a double angle formula in it. We'll see. I might do it 2 ways. Okay, this is going to be indeterminate. Okay, I think this time I'm going to start doing this thing, the cosine of 2x. I'm going to use the double angle formula for cosine, and I'm going to use the format that uses sine because it's going to most resemble what I'm trying to get here. So let me leave the numerator the same. For the denominator, the cosine of 2x, if you look at the list of identities, I can make it 1 minus 2 sine squared x, which looks like it is related to the numerator. So it seems like it is actually a good idea to go this way. Okay, I'm going to try to factor the denominator. Okay, now it's kind of a difference of squares. It's 1 minus something sine x. It's going to be 1 minus root 2 sine x. When we're done, we'll stare at this and make sure it looks right. Okay, 1 times 1 is 1 plus root 2 sine x minus root 2 sine x cancels. And then if I do this times this, root 2 times root 2 is minus 2. Sine times sine is sine squared. So it does in fact match. And then I can see I can cancel that factor right there. So I'm left with 1 in the numerator and 1 plus root 2 sine x. Okay, and I did take this all the way to the simplified format before I did direct substitution. Now I'm going to do direct substitution. 1 plus root 2 times the sine of pi over 4 is root 2 over 2. See, 1 plus 1 is 2. So the limit is 1/2 after all that